Hello, this is Mr. Henry, and welcome to lesson 6.2. We're going to use functions to model relationships. The central question says, well, how do I use functions to model relationships? I'm pretty sure all the relationships we're going to look at in this lesson are all linear. So we'll be looking at lines, equations of lines, and that sort of thing. Okay. Did you know that linear functions are often used to represent situations where something is increasing or decreasing at a constant rate? I'm going to actually underline that phrase, constant rate. That is kind of important. A constant rate means a rate that doesn't change. Okay? So for example, if you get paid $8.50 an hour, you get paid that the same rate all the time. Every single day, you get paid $8.50 an hour, $8.50 an hour. That would be a constant rate. Now, if, say, like you're a waiter or a waitress, you don't always get paid a constant rate. If you have a busy night and people are tipping better, you make more money. That's not a constant rate. You can't always make a good prediction on how much money you're going to make at the end of the night. Okay? So, if I actually complete the example and read on, it says getting paid $8.50 an hour, a machine making 3,000 Hershey Kisses an hour. I mean, that machine, if that's what the machine is set at, it will make those 3,000 kisses every hour. That's a constant rate. A car traveling at a constant rate of 65 miles per hour. So if you put the cruise control on your car, and it's just going at that same speed all the time. Now, each of these scenarios have initial value, which is like how much money you start with or how far you've already traveled. And they also have a rate. A rate is how fast is something changing. How fast is your money changing is your rate. How fast is the number of Hershey Kisses changing? How fast is your distance changing? That's a rate. Okay? We've got two vocab words here. We've got a linear relationship and initial value. So a linear relationship is a relationship that can be written in the form y equals mx plus b. That should be familiar. We did that back in chapter 3 or chapter 4. That's a while ago now. So that's slope-intercept form. That is the equation of a line. So if you can write something and it looks like that, that means you have a line, and therefore it is linear. Okay? Initial value. An initial value, as the name suggests, is the value at the beginning of the problem. That's what the word initial means. Initial means the beginning. So like the initials of my name are S.H. Sean Henry. The initial is the first letter of each name. Okay? Initial means first, means beginning. So when we're talking about our functions, that will always happen when the value of the function, or in the value of function when x is 0. X being 0 is like, think of it like at time 0, at the beginning of the problem, how much money do you have, or how many Hershey Kisses have been made, or how far are you from home, okay? So the initial value is how much of whatever you have in the problem do you have at the beginning. And that is your y-intercept. The y-intercept is a nice, easy way to start graphing a function if you need to. So let's see how these are used in action. So first example here says, Jasmine is currently 200 miles away from home. She's trying to get home and traveling 60 miles per hour. Identify the initial value, the rate of change of the function, and then write an equation in slope-intercept form to represent this situation. Okay, so I'm going to start with finding my initial value and my rate of change. So the initial value is at the beginning of the problem, how far away from home is she? Because that seems to be what's that's changing, right? Her distance away from home. So the initial value is how far away from home is she? Well, she is currently 200 miles away from home. That's the initial value. At the beginning of the problem, she's 200 miles away from home. Now, how fast is that changing? What is her rate of change? Well, that distance is changing at a speed of 60 miles per hour. So every hour, this number is going down because she's going home. Her rate of change is going down by 60 miles every hour. So her rate is 60 over 1. And I'll be honest with you, it's not actually quite 60. It's a negative 60. You go, why the heck is it negative? It'll make much more sense here in a second. Okay, let's write the equation, and then I'll talk about why that rate of change, why the slope is negative. So it wants us to write the equation in slope-intercept form. So that was that y equals mx plus b. So the rate of change is your slope. This word rate, think of that. Rate is slope. Rate is slope. When you hear the word rate, I want you to think of a slope. And your initial value is your y-intercept. Okay? So with those two pieces in mind, you should be able to very quickly plug in the equation y equals negative 60x plus 200, where this is your slope and this is your y-intercept. Now, I said I was going to explain why that slope was a negative 60, not positive. Because like here it goes, oh, she's trying to get home and traveling 60 miles per hour. You think, would that be a positive 60? No. Because let's think about this. If I erase this 60 for a second, or that negative for a second. If I just plug in a number and see what happens. Let's say she's been driving for 1 hour. And I do the math. She's driven for 1 hour. 60 plus 200, and I do the math. Y equals 260. So after she's been driving for an hour, is she 260 miles away from home? I hope not. If she is, she's not doing a very good job driving home. If we put in here 2 hours, 2 times 60 is 120. Now I could do it this way, I guess. 120 plus 200 gives us, now she's 320 miles from home. She's doing an awful job getting home. Okay? Now, because the distance away from home, this is how far she is from home. Because that number is going down every hour, that means our slope should be negative. Her distance from home is decreasing over time. It's going down. So if I throw in a negative in here, now if she's been driving for 2 hours, this would give me negative 120 plus 200. That means she's now only 80 miles from home. That makes a lot more sense. She's now much closer to home than she was. Okay? So the reason why this is a negative is because her distance from home is decreasing. It's going down. That's why it's a negative. If her distance from home was increasing, it'd be a positive slope. Okay? So the things they wanted us to find here. Initial value. Boom. Rate of change. Boom. Equation of line. Boom. Letter B. Letter B. Last summer, Sean had a banister put on the front of his house. The carpenter charged a fee of $120 for materials and $100 per hour to rip out the old banister and put in the new one. Identify the initial value and the rate of change. Then graph the function. Okay, so the verbs. They want me to identify the initial value, the rate of change, then graph the function. Those are my verbs. That's the things they want me to do. So I want to find initial value, rate of change, and then I need to graph it. Okay, so the initial value. Initial value, reminder, is your y-intercept. It's what happens at the beginning of the problem. Okay. In the beginning of the problem, let's see, last summer Sean had a banister put on his house. The carpenter charged a fee of $120 for materials and $100 per hour to repair the banister. So, at the beginning of the problem, how much money did Sean owe? Well, he owed $120. And then, how fast is that rate changing? What is the rate that these carpenters are charging? Well, they're charging $100 per hour. That, whoa, wrong letters, wrong order. Slope. That is our rate, $100 per hour. Okay. So, initial value, check. Rate of change, check. Graph the function. Now, in order for me to graph this, I would like to get my equation. So my equation in the formula, y equals mx plus b. So I have y equals my slope. The slope comes first. My slope is 100x. My initial value is 120. Now, before I go further, I'm just going to ask myself. This guy, so Sean has to pay $120 for materials up front, right? And then he's getting charged another $100 per hour. Is the amount of money Sean has to pay going to increase every hour, or is it going to decrease every hour? I'm asking because it makes a difference whether our slope is positive or negative. So is his total fee going to keep increasing, or is it going to be decreasing every hour? It should be increasing. So we should have a positive slope, which we have here, and we have here. Okay, so I think we're ready. So my x variable, well, if my initial value is $120, that's the y-axis over here. So I need to have $120 here. So this is my dollars. I can't write sideways on this tablet, so I'm just going to go like this. Boom. There's my dollars. And my y variable would be time, hours. Time is always the independent variable. Time will always be on the x-axis. Okay? X, y, if it makes you feel good. Okay, now we need some scales. I need to have, well, I should probably think about this, because if I go and I start counting by, like, say, 20s. 0, 20, 40, 60, 80, 100, 120. If I put 120 here, that's not going to work out so well for me. Let me show you why. Don't write this. Do not write this. If I do this, 0, 20, 40, 60, 80, 100, 120, 140, 160, 180, 200. What's going to happen here, even if I just go like this 1, 2, 3 hours, at hour 0, my initial value is 120. If I do this, now, if I go 1 hour further, I need to have another $100. I need to go up $100 over 1. I'm already off my graph. I didn't plan ahead very well. I didn't look at that my slope means I need to go up 100 over 1. So this scale here is not going to be so good. So what I should probably do is I should probably count by something larger. Give me more space. So maybe if I count by, say, 50s or hundreds. I'm going to do 50s, I think. So 50, 100, 150, 200, 250, 300, 350, 400, 450, 500. That will get me at least a couple hours of work. Whoa. Whoa. 4, 5, 6, 7, 8, 9, 10. And I'm not going to get the whole way out here. I don't expect to. Okay, so now, if I start doing this, at hour 0, $120. So just a little bit above 100. Not quite up to 150. Maybe a teensy bit higher. There. Now, if I go, my slope is 100 over 1. So I'm going to go up $100 over 1 hour. So 1 hour of work, Sean would owe these guys $220. Now, if I go up if they work another hour, up $100 over an hour. So in 2 hours of work, it's now $320. Up 100 over 1. Up 100 over 1. Now if you look, my line's perfectly straight. It is linear. I can draw, use a straight edge if you need to. I've got my beautiful line tool here. A nice straight line through your points. That is the graph of this function. Okay, so I'm able to find my initial value at the beginning of the problem. Sean owed the guys $120. My rate of change, every hour they charge me another $100. That translates into our slope and our intercept. Letter C. Here we go. A farmer is harvesting corn from his field. The graph below shows the amount of corn still in the field while the farmer is harvesting his field. Write the function, there's a verb, write the function that is represented by this graph. Identify the rate of change and the initial value. So I have to do three things. Write the function, identify the rate of change, and the initial value. So very similar to the previous problems. Okay, so let's see if I can do that. So initial value. Reminder, that is my y-intercept, the amount of stuff at the beginning of the problem. My rate of change. That is my slope. Also, sometimes the speed of the problem, how fast the thing is changing. And then lastly, I need my equation in slope-intercept form. Okay, so let's see what we can come out of from this graph. So my initial value, can I find my y-intercept by looking at my pretty picture? Yes, it's very easy, very easy. It's right there. So my line, my function, my relation is crossing the y-axis at the number 4,000. So there's 4,000 pounds of corn in the field at the beginning of the problem. Now, as the guy's harvesting, look what's happening to the corn. It's going down over time. Well, how fast is he plucking the corn from the field? I have to find the slope. So if you remember when we found slope from graphs before, I like to do something I call the counting box method. So I'm looking for where does my line go right through those lattice points. And I see there's one. Well, here. No, no. He's close. No. Ooh. I would call him right on. No, 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 no. Yes. Now, if you're looking at this and you're going, hey, I bet my slope's down to over 5. Well, you're sort of right, but still very wrong. Yes, you go down 2 boxes, down 2, and you go over 5 boxes, but when you're going down 2 here, you're not actually going down 2. You're not just taking out 2 pounds of corn in 5 hours. You're taking out 2,000 pounds. You're going from the number 4,000 to the number 2,000. So it's down 2,000 pounds over, this is actually 5 hours. 1, 2, 3, 4, 5. So the scale down here is kind of by ones. So my rate of change is down 2,000 over 5, which we could probably simplify, right? I mean, they're both divisible by 5. I don't feel like doing math in my head. Negative 2,000 fraction 5 equals, there we go, negative 400. I should have known that. Oh well. So that would mean, and if you want to keep it as a fraction, you can. That would mean every hour they're taking out this much corn. So every hour, they're taking out 400 pounds of corn. So I have my initial value, how much corn is in the field at the beginning of the problem. I have my rate of change, the speed at which they're taking the corn out of the field, and that gives me my equation, y equals negative 400, that's my slope, my speed, my rate, x plus 4,000. That's my initial value. So this is my slope-intercept form, also my rate initial value form. In that last problem, the corn problem, what does the rate of change mean in the scenario? I think I might have even told you the answer just not too long ago. What does this rate of change, what does this negative 400 over 1 mean in terms of this farmer getting corn out of his field? What does that mean? We're trying to interpret the rate of change, interpret the slope. Well, that's the speed at which he's harvesting. That is the speed. He's harvesting 400 pounds of corn in 1 hour. That's what that slope means. That's what that rate of change means. He's harvesting 400 pounds of corn from the field every hour. That's what it means. That is the rate of change. Okay? Rate of change is a speed, how fast something's changing. Love it. All right, letter D. We are flying. Letter D says, Derek works on an assembly line, putting together electronics for an engine. He gets paid a daily wage, plus an additional amount for every engine he puts together. The table below shows his daily earnings, Y, if he puts X engines together. So, lots of story. I haven't heard any verbs yet, things they want us to do. Oh, there it is. Write a linear function. So that's our equation. That's the function that models the situation. Identify the initial value and the rate of change. Then graph. Holy cow. So they want me to do 4 things in this problem. Write the equation, find the initial value, find the rate of change, graph the function. Okay. Well, I'm looking at this, and I'm looking saying, okay, can I write the equation from this right away? Not really. I mean, we can't really write the equation until we have the initial value and the rate of change, because that's my slope and my y-intercept. So if I find slope and intercept, then yeah, I can write the function. And I'm looking at the table give me. Does it give me my initial value? Does it give me my y-intercept right away? No. I'm looking at my rate of change. Does it give me the slope? No. Can we find those things? Yeah, absolutely we can. So let's do that. So first off, rate of change, slope. I need to find the slope from this table. We have done that in the past. We have found slopes from sets of points. So I'm just going to pick 2 points that I like. I like him. And I don't know. I like him. Why not? I'm just picking any 2 random points. It doesn't matter which 2 you pick. Okay? And I'm going to use my formula. M equals y2 minus y1 over x2 minus x1. Whoa, way back when we were talking about slopes, that is a formula we use for finding slope. It's not gone. It's not dead. We're still using it. Don't forget it. If you forgot it, it is on the formula sheet. And if I use these 2 points, with this being my x1, and these are my y1, x2, y2, because these are my x variables, these are my y variables. If I plug those in, y2 minus y1 over x2 minus x1. And I math. The math on the bottom is easy. And my brain's not working so well. The math on the top is not so easy. I lied. I think it's probably 11, right? Double check, 'cause I don't want to be stupid and make a dumb mistake, and it screws me the rest of the way of the problem. Good. All right. Good. My brain's not completely fried yet. So it's 11. Okay. We found the slope, which I guess if my job somewhere here is to write the rate of change, which is slope, and there's supposed to be a G in change, which is a speed. I found the change is 11 over 1. Okay, cool. I found slope. Can I find my y-intercept? Can I find my initial value? Yeah. I hope you remember doing this. So, remember if we had a formula and we found the slope. Do you remember how we can find this guy? We took one of our points and we plugged it in for x and y. So I'm going to take my first point that I use here, this 2, 152. So I'm going to plug in 2 for my x variable, and I'm going to plug in 152 for my y. See? X variable in for x, y value in for y. And if I solve this little dinky equation, it will give me my y-intercept. Okay, 2 times 11 is 22. If I subtract 22 on both sides, b is equal to 130. I have found my y-intercept, which is my initial value of 130. So that means initial value. At the beginning of the day, we're talking about money, this guy gets paid 130 bucks. And then the speed at which his money changes, it changes by 11, let's check my units are, $11 per engine. So this is dollars. This one is engines. That's how fast his money's changing. So he starts with 130 bucks, and then he makes $11 for every engine he puts together. And now that I'm thinking about it, look at this. I got a y-intercept. I got a slope, which means I can write the equation of this line, which I kind of almost already did. So the equation of this line, y equals mx plus b, y equals, I'm out of space, y equals 11 x plus 130. Boom. I've got function. I've got rate of change. I've got initial value. The only thing I haven't done is I haven't graphed it yet. But now that I have all this stuff, it's going to be easy. So, 0, 0. My scale, I got to get up to around here, so I'm going to count by 20s. Because if I count by 20s, that gets me up to 200. 2 times 10. Yeah, so or 2 times 10, there's 10 lines times by 20 is 200. So if I go 20, 40, 60, 80, 100, 120, 140, 160, 180, 200. And I only need to get up to 5 hours, so 0, 1, 2, 3, 4, 5, and a bonus for good luck. This number is our engines. This number over here is our dollars. And we're good to go. So I know he starts out at 130 bucks, right? That's what we found down here. We found the y-intercept is 130 bucks. And now, at 1 hour, he makes 141. 2 hours, he makes 152. At 3 hours, it's 163. 4 hours is 170. So remember, this is 180, so 170 is halfway. So I'm just going, here's 170, 174. 5 hours, 185. If this is 180, here would be 190, so about there. And if I use my pretty little line tool, oh, would you look at that? They line up. And they should, because it is a line. It is linear. See the equation? Linear. So I wrote the equation. I found the initial value. I found the rate of change. I graphed the function. I have done everything they've asked me to do. So I think we're ready to move on to the next problem. By the way, another way you could have found the initial value, if this thing down here you didn't really like, you could have looked at this graph and go, okay, after you found the slope is 11, you found this pattern. The pattern here is plus $11, plus $11, plus $11. You could work backwards and say, okay, well, if he puts together 0 engines, how much money does he make? Well, if you work backwards, minus 11, minus 11. Well, from here, if you minus $11, it gets you 130. So at 0 engines, he makes 130 bucks. That's another way to find that same y-intercept, just a slightly different method. Ooh, we got some problems based off. Okay, so it says, what does the initial value represent in this scenario? So let's go back. In my scenario here, what is the initial value? We said the initial value was 130 bucks. We also said it's the y-intercept. Okay, so what does that number mean in terms of Mr. Derek here and him making money putting engines together? Give you a hint. That's how much money he makes when he hasn't put together any engines. He gets paid $130 just for showing up to work. Okay? Now, I know some 8th graders out there going, heck, I get paid $130 just for showing up. I'm not going to put together any engines. I'll just get paid the 130 bucks. No, that's how you get fired. So you start with that much money, but the more you put together, the more money you get. And so it's kind of an incentive to work harder and work faster. But if you don't put together any engines together for a couple days, they're going to catch on and you're fired. You don't make any more money. Okay, so the initial value is his daily wage. That's how much money he gets paid at the beginning of the problem. Okay, next question says, what does the rate of change represent? If we go back, we said the rate of change was 11 over 1. That's the slope, the speed. I even have some units here. So that rate of change is the amount of money he makes for each engine. So he makes $11 for putting together one engine. What does the rate of change represent? Money made for each engine he puts together. Okay, so that's what our rate of change is. It's the amount of how fast his money changes for each engine he puts together. Look at this. I think we're in our last problem already. Letter E. When the police find a dead body, they will often use the temperature of a person's liver to find their time of death. The graph below shows a person's liver temperature after their death with respect to time. Identify the initial value and rate of change. So if I'm looking for those verbs for you, identify the initial value and rate of change. Then write the equation in slope-intercept form. Okay? So those are the three things you've got to do. Find the initial value, find the rate of change, write the equation in slope-intercept form. So pause the video, do the problem on your own. When you're ready to continue, hit play, and we'll go through it together. Okay, So let's see what you come up with. So, like before, we can't really write the equation until we find these other two guys. So we need to find the slope and the intercept to write the equation in slope-intercept form. So I'm going to start with, well, initial value. My initial value is still my y-intercept. It's still the value at the beginning of the problem. My rate of change is still the slope of the line, or the speed at which the thing is changing. In this case, we're talking about the liver temperature, how fast the liver temperature is changing. And then finally, I'm going to need my equation of the line. All right, so my initial value. I'll be honest, I can kind of get that from my pretty picture. I can't get it exact, but I can get pretty close. I mean, right there. My line is crossing the y-axis right there. Now, get my marker out of the way again. I would guess that's about 37, 38. That's a reasonable guess. 37, 38. Rate of change. How fast is that changing? Well, if I go from... Whoa, I missed. If I mark 2 points, there's this one here, right there. See it? It's going right through the little crisscrossy. And I'll be honest, it looks like there's another one over here somewhere. If I go from here to here, if I'm calling this number 37, then from this dot to this dot is down 7, because from 37 down to 30, down 7 over 5. Down 7 over 5. That would be my rate of change. That would be the speed. Now, I'm curious if that's the same over here. This is, what, down 10 over 6? I don't think that's the exact same thing. How close is it? Negative 7 divided by 5. Negative 10 divided by 6. Okay, so somewhere between there and there is my actual slope. What if what if this is like, say, negative 8? What if that number is 38 instead of 37? What is negative 8 divided by 5? That's pretty darn close. Let's do that. Let's call him 38, because it makes our slope a little bit prettier. So now it's down 8 over 5, down 10 over 6. Yeah, it all works out to about the same. Okay. So if I got my initial value, I've got my rate of change. I got both of those things from just looking at the picture. So the equation of the line, of this line right here, would be y equals negative 8/5 x plus 38. So that would be the equation that a coroner would use to determine the time of death of a body that they find. What does the initial value mean in this situation? So let's go back. Initial value, we said, was 38. What does that number 38 mean? Well, it's the value at the beginning of the problem. It's the liver temperature at time 0 after death. So that's the person's body temperature as soon as they've died, or you could also say somebody who's alive. If we do, Mr. Google here, human body temp in Celsius. I just put C. Google knows what I mean. So the average normal body temperature is generally accepted at, look at that, 37 degrees Celsius. I should have stuck with what I started with. I changed it to 38. And it goes on and on and on, talks about it, but good old Google, roughly 37, 38 degrees Celsius. I rounded it up to 38. Okay. Should have stuck with my gut and went with 37, but that's okay. It's no big deal. Okay, so the initial value, that 38 that I had, is the temperature of a human body as soon as they've died. So the value of a person's body when they're alive. make sure you put that in there, because we're done. Lesson 6.2 summary says, in what ways did we use functions to model relationships throughout this lesson? So how did we do it? What did we look for? What characteristics did we use? Give you a hint. Initial value, rate of change. How did we use those things? Okay? This has been lesson 6.2. Thank you for watching.